Welcome to Cloud CDN Mastery. Welcome to the channel. Please consider subscribing to the channel. I produce videos daily covering cloud topics with focus on networking. Today I will cover Google Cloud CDN, from basic concepts to advanced enterprise implementations. Today's session is designed for both beginners and experienced engineers. We'll start with the fundamental why behind CDN. Then dive deep into hands-on configuration with real G Cloud commands you can run in your own projects. By the end of this presentation, you'll have practical experience setting up CDN with multiple origin types, implementing security with signed URLs, managing cache invalidation, and troubleshooting common issues. What makes this different from typical CDN tutorials is that we'll explain every single command parameter, explore the decision-making process behind architectural choices, and share real-world gotchas I've encountered in production deployments. Let's transform you from someone who's heard of CDN to someone who can architect and implement global content delivery solutions with confidence. Why CDN matters. The Global Performance Challenge. Let me start with a story that will make CDN concepts crystal clear. Imagine you've built an amazing web application and deployed it on a single server in Virginia. Your New York users are thrilled. Pages load in 50 milliseconds. But then you get users from Tokyo, and they're complaining. Your beautiful app takes 800 milliseconds to load. That's not because your code is slow. It's pure physics. Data traveling from Virginia to Tokyo has to cross continents and oceans. Now picture this. Instead of one kitchen serving cold pizza worldwide, you have local kitchens in every major city. The Tokyo customer gets hot, fresh pizza from the Tokyo kitchen in 5 minutes, not 2 hours from New York. This analogy maps perfectly to CDN. Your origin server in Virginia is the main kitchen. Google's 100+ edge locations worldwide are the local kitchens. When someone in Tokyo requests your logo.png, they get it from Tokyo's edge cache, not Virginia. The beauty is this happens automatically. You don't manage 100 servers. Google does. You just enable CDN, and suddenly your single server application becomes a globally distributed, lightning-fast experience. Cache hit versus miss. The core decision logic. Every CDN request follows the same fundamental decision tree, and understanding this is crucial for optimizing your CDN performance. When a user in Tokyo requests /images/logo.png, Google's Tokyo Edge Cache becomes the decision maker. It asks itself, do I have a fresh copy of this file? If yes, that's a cache hit. It serves the file instantly from local storage. This is the best case scenario: sub-millisecond response times and zero load on your origin server. If no, that's a cache miss. The Edge Cache becomes a smart proxy. It fetches the file from your origin server, stores a copy locally with a TTL time to live, then serves it to the user. Here's the key insight. The first user after a cache miss experiences slower loading, but every subsequent user gets lightning-fast delivery. The Edge Cache learns what content is popular and keeps it ready. In production, you will typically see 85 to 95% cache hit rates, meaning most of your traffic is served instantly from edge caches rather than hitting your origin servers. This dramatically reduces server load and improves user experience. Business impact. Why CDN drives revenue. Let me share some real numbers that make the business case for CDN implementation crystal clear. Performance impact is measurable and significant. Amazon found that every 100 milliseconds of latency costs them 1% in sales. Google discovered that increasing search results time by 400 milliseconds reduced searches per user by 0.59%. For a typical e-commerce site, CDN can reduce page load times by 60 to 80%. Cost reduction is immediate and ongoing. Without CDN, every image, CSS file, and JavaScript request hits your origin servers. With CDN, more than 90% of requests are served from Google's Edge network. This means you can run smaller, cheaper server instances while serving more users. Scalability becomes effortless. Remember the last time a website went viral and crashed from traffic? With CDN, Google's global network automatically absorbs traffic spikes. Your origin servers stay happy while serving millions of users. Reliability improves because cached content can be served even if your origin servers experience issues. I've seen companies maintain 99.9% uptime during origin outages because their static assets continued serving from CDN caches. Security gets a boost too. Google's Edge network includes DDoS protection and can absorb massive attacks before they reach your infrastructure. Architectural flexibility. Origin's deep dive. One of Cloud CDN's greatest strengths is its flexibility in supporting different origin architectures. Let me walk you through each option and when to use them. Cloud storage buckets are perfect for static content, images, videos, CSS, JavaScript, downloadable files. They're the easiest to configure and most cost-effective. I use these for marketing sites, documentation, and any content that doesn't change frequently. Managed instance groups work brilliantly for traditional web applications. If you have PHP, Python Django, Ruby on Rails, or any server-side rendered application, this is your go-to. The CDN caches your dynamic responses, reducing database load. Cloud Run represents the modern serverless approach, perfect for containerized APIs, microservices, or any application where you want zero server management. The combination of serverless scaling with global CDN caching is incredibly powerful. External origins are the game changer for multi-cloud or hybrid architectures. You can use AWS S3, Azure Blob Storage, or your on-premises servers as origins. This means you don't need to migrate existing infrastructure to benefit from Google's CDN in large enterprises. I often see hybrid approaches. Static assets in cloud storage, APIs on Cloud Run, and legacy applications on Compute Engine, all fronted by a single CDN-enabled load balancer. Foundation setup. Getting your environment ready. Before we create our first CDN setup, let's establish a rock-solid foundation. This preparation phase is absolutely critical, and it will save you hours of troubleshooting later. Setting the projectID environment variable isn't just about convenience. It's a best practice that prevents errors. I've seen countless deployments fail because someone typed the wrong project name in a command. The export command stores your projectID in memory for the entire session. The gcloud config set project command tells the Google Cloud SDK which project to use as the default for all subsequent commands. This is your safety net. Every resource will be created in the correct project. API enablement is often overlooked, but it is essential. Google Cloud uses APIs to control access to different services. The compute.googleapi.com API gives you access to load balancers, instance groups, and CDN functionality. The storage.googleapi.com API is needed for cloud storage buckets. The run.googleapi.com API enables Cloud Run services. These APIs can take 1 to 2 minutes to fully activate after enabling, so it's worth running these commands first and then taking a coffee break. Trust me, trying to create resources before APIs are active leads to cryptic error messages that waste time. Once these prerequisites are in place, you have a solid foundation for any CDN architecture we'll build today. Cloud Storage CDN, the static content powerhouse. Let's start with the most common and straightforward CDN implementation, using cloud storage as our origin. This approach is perfect for static websites, image galleries, video libraries, and downloadable content. The gsutilmb command creates a new bucket. Notice we're using a globally unique name that includes the project ID. This prevents naming conflicts since bucket names must be unique across all of Google Cloud. The MB stands for Make Bucket, similar to mkdir for directories. The IAM command is crucial for CDN functionality. The All Users Object Viewer permission makes every object in the bucket publicly readable. Without this, your CDN can't serve content to users. This is equivalent to making a web server directory publicly accessible. Creating and uploading sample content gives us something to test with. In production, you'd upload your actual static assets, such as CSS files, JavaScript libraries, images, videos, or any downloadable files. The backend buckets create command is where the CDN magic happens. Unlike a regular backend service for virtual machines, backend buckets are specifically designed for cloud storage origins. The Enable CDN flag is what activates CDN caching for this bucket. This single flag transforms a simple storage bucket into a globally distributed CDN origin. The URL map creation establishes the routing rules for our load balancer. In this simple case, we're sending all requests to our backend bucket, but URL maps can handle complex routing scenarios with multiple backends and path-based routing. Managed instance groups. Building virtual machine infrastructure. Now let's build a more robust CDN origin using Compute Engine virtual machines. This approach is perfect for dynamic web applications that need server-side processing, database connections, or any traditional web application architecture. Instance templates are the foundation of managed instance groups. Think of them as blueprints that define exactly how each virtual machine should be configured. The machine type E2 Micro is cost-effective for demos, but production workloads typically need E2 medium or larger instances depending on your application requirements. The image family Ubuntu 2004 LTS ensures we get the latest patched version of Ubuntu 20.04. Using image families instead of specific image names means Google automatically gives us the most current version with security updates. The startup script is incredibly powerful because it runs automatically every time a virtual machine boots. This script updates the package manager, installs Nginx web server, and configures it to start automatically. In production environments, you would include your application deployment, configuration management, and monitoring setup here. Creating the managed instance group with size 2 gives us redundancy. If one virtual machine fails, the other continues serving traffic. The zone placement determines where these virtual machines run physically. Choose zones close to your primary user base for optimal performance. Health checks are absolutely essential for any load-balanced system. This HTTP health check sends periodic requests to port 80 at the root path of each virtual machine. If a virtual machine does not respond correctly within the timeout period, it is automatically marked unhealthy and removed from traffic rotation until it recovers. Backend service integration. Connecting virtual machines to the CDN. Now we need to connect our virtual machine infrastructure to the load balancer and enable CDN functionality. This is where we transform individual virtual machines into a globally distributed, cached service. The backend service acts as the logical connection point between the load balancer and your virtual machine instances. The protocol HTTP tells the load balancer how to communicate with your virtual machines. This must match what your application serves. Associating the health check with the backend service is critical. The load balancer uses this health check to determine which virtual machines are healthy and should receive traffic. Without proper health checks, users might get routed to failed instances. The Enable CDN flag is what transforms this from a simple load balancer to a globally cached CDN once enabled. Responses from your virtual machines will be cached at Google's edge locations worldwide, dramatically reducing response times for subsequent requests. Adding the instance group to the backend service completes the connection. The instance group zone parameter tells the load balancer exactly where to find your virtual machines. You can add multiple instance groups from different zones for even better redundancy and performance. The URL map creation establishes the routing rules. In this simple case, all traffic goes to our web backend service, but URL maps support complex routing scenarios with multiple backends based on paths, headers, or other criteria. Cloud Run. Serverless CDN at scale. Cloud Run represents the cutting edge of serverless architecture combined with global CDN caching. This approach is perfect for modern containerized applications, APIs, and microservices where you want zero infrastructure management. The G-Cloud Run Deploy command is deceptively simple but incredibly powerful. We're using Google's sample Hello container, but in production you'd reference your own container image from Container Registry or Artifact Registry. The platform managed means Google handles all the infrastructure, no servers to manage, patch, or scale. The region US Central 1 determines where your service runs by default, but Cloud Run can automatically scale to other regions based on demand. The Allow an Authenticated flag makes the service publicly accessible. For CDN origins, this is typically what you want. The Network Endpoint Group creation is the bridge between your serverless Cloud Run service and the traditional load balancer infrastructure. The Network Endpoint type serverless tells Google this isn't a traditional virtual machine-based service but a managed serverless endpoint. Creating the backend service with Enable CDN is where we get the best of both worlds, the scalability and simplicity of serverless combined with the global performance of CDN. Your Cloud Run responses get cached at edge locations worldwide. Adding the NEG to the backend service completes the connection. The Network Endpoint Group region parameter tells the load balancer which region contains your Cloud Run service. This setup automatically handles traffic routing and scaling. What's truly powerful here is that Cloud Run automatically scales from 0 to thousands of instances based on demand, while CDN reduces the load on your service by serving cached responses. You get infinite scalability with minimal operational overhead. HTTPS Load Balancer completing the CDN pipeline. Now we are going to complete our CDN setup by creating the HTTPS load balancer components that actually receive traffic from the internet and route it through our CDN-enabled backends. SSL certificate creation is the foundation of HTTPS. The managed certificate type means Google handles the entire certificate lifecycle: creation, validation, renewal, and revocation. You never have to worry about expired certificates bringing down your site. The domains parameter is critical and must match exactly what users type in their browsers. If you plan to serve content from both www.example.com and example.com, you need both domains in the certificate. Wildcards like wildcard.example.com work for subdomains but require DNS verification. Certificate validation happens through DNS records that Google creates automatically. The process can take 10 minutes to several hours depending on your DNS provider's propagation speed. During this time, HTTPS will not work, so plan accordingly for production deployments. The target HTTPS proxy is where SSL termination happens. It decrypts incoming HTTPS traffic and forwards HTTP requests to your backends. This proxy also handles HTTP/2 and QUIC protocols automatically for better performance. The global forwarding rule creates the public IP address that receives internet traffic. Port 443 is the standard HTTPS port that browsers connect to. The global scope enables Anycast routing users automatically connect to Google nearest edge location. Getting the IP address is essential because this is what you will point your DNSA record to. Once DNS propagates and the SSL certificate validates, you will have a complete production-ready CDN implementation. CDN verification. Proving cache performance. Verification is where theory meets reality. We need to prove our CDN is actually working and providing the performance benefits we expect. This process teaches you how to troubleshoot CDN issues in production. The curl command with specific flags gives us detailed information about the HTTP transaction. The -s flag makes it silent, no progress bar. -o dev/null discards the content, we only want headers. And -d dumps headers to standard out. The age header is the smoking gun that proves CDN functionality. When age is 0, the content was fetched fresh from your origin server, either because it's the first request or the cache was empty. When age shows a positive number, that's how many seconds the content has been sitting in the edge cache. The first request should show age. 0 and potentially longer response times as the edge cache fetches from your origin. The second identical request should show age greater than 0 and much faster response times. This proves content is being served from the edge cache. Other important headers include via, which shows Google's proxy servers in the path, and cache control headers from your origin that influence caching behavior. Understanding these headers is crucial for optimizing cache performance. In production environments, you'll want to monitor cache hit ratios through cloud monitoring. Typical production sites see 85 to 95% cache hit rates. Lower ratios might indicate misconfigured cache headers or content that changes too frequently to cache effectively. The logging command shows you real request data flowing through your load balancer. This is invaluable for debugging route issues, monitoring traffic patterns, and understanding user behavior. External origins. Multi-cloud CDN architecture. One of Cloud CDN's most powerful features is the ability to accelerate content from external origins, such as AWS S3, Azure Blob Storage, or your on-premises servers. This enables multi-cloud and hybrid architectures without vendor lock-in. This architecture diagram shows how Google's CDN can sit in front of any origin, whether it's in Google Cloud or completely external. The key insight is that users always connect to Google's fast edge network, regardless of where your content actually lives. Multi-cloud strategies are increasingly common in enterprise environments. You might use AWS for primary storage due to existing contracts, but want Google's superior global CDN performance. Or you might be gradually migrating from on-premises to cloud and need CDN during the transition. The beauty of this approach is that it's completely transparent to users. They get the same fast performance whether your origin is in Google Cloud Storage, AWS S3, or your data center in Tokyo. The CDN abstracts away the complexity of your backend infrastructure. This flexibility also enables sophisticated content strategies. You could serve static assets from S3, APIs from Google Cloud Run, and legacy content from on-premises servers, all through a single CDN-enabled load balancer with consistent performance worldwide. Security considerations are important here. External origins need to be publicly accessible for CDN to work, which might require firewall changes or security group modifications in your existing infrastructure. Internet NEG. External service integration. Let's dive deep into configuring Internet NEGs for external origins, using AWS S3 as our example since it's the most common multi-cloud scenario I encounter. The network endpoint groups create command establishes the logical connection to your external service. The name should be descriptive since you might have multiple external origins for different content types or regions. The Internet_FQDN_ port type is specifically designed for reaching services outside Google Cloud. This is different from Internet_IP_port, which requires static IP addresses. Most cloud services use DNS names that might change over time. Port 443 is standard for HTTPS connections, but some services might use different ports. Custom applications on non-standard ports work fine as long as they're publicly accessible. The global flag is mandatory for CDN integration. The update command with add endpoint actually configures the target service. The FQDN must be the exact domain name that serves your content. For S3, this is the regional endpoint that ensures consistent routing and performance. Backend service creation follows the same pattern as internal origins, but the protocol specification becomes more important. If your external origin serves HTTPS, use HTTPS protocol. If it serves HTTP, use HTTP protocol. But remember that CDN will still serve HTTPS to users. The custom request header configuration is often critical for external origins. Cloud storage services frequently use the host header to route requests to the correct bucket or container. Without this header, requests might fail or serve incorrect content. This setup enables powerful hybrid architectures where you can gradually migrate content to Google Cloud while maintaining existing external systems, or create multi-cloud redundancy strategies. Advanced CDN configuration, optimization and security. Once you have basic CDN functionality working, there are several advanced configurations that can dramatically improve performance and security for production workloads. Cache mode configuration controls how aggressively CDN caches your content. Cache all static caches based on file extensions and response headers. Use origin headers respects cache control headers from your origin. Force cache all caches everything regardless of headers. Useful for APIs that don't set cache headers correctly. TTL settings control cache duration. Default TTL applies when your origin doesn't specify caching headers. Max TTL prevents origins from setting excessively long cache times. Client TTL controls what browsers cache locally. This can reduce CDN requests for repeat visitors. Cache key policies determine what makes content unique for caching purposes. Including the host allows the same CDN to serve multiple domains. Including protocol keeps HTTP and HTTPS responses separate. Query string handling is crucial. Exclude them for static assets, but include them for dynamic content that varies by parameters. Negative caching handles error responses like 404 not found. By default, CDN doesn't cache errors, which means repeated requests for missing files hit your origin. Enabling negative caching with short TTLs can protect your origin from repeated requests for missing content. Security policies can be attached to backend services for DDoS protection, rate limiting, and geographic restrictions. These policies are evaluated before requests reach your origin, providing an additional security layer. Monitoring setup through cloud monitoring gives you visibility into cache hit ratios, error rates, and traffic patterns. These metrics are essential for optimizing cache configuration and identifying performance issues before they affect users. Cache invalidation. The corporate recall notice. Cache invalidation is one of the most critical operational skills for managing CDN in production. Think of it like issuing an urgent corporate recall notice. You're telling Google's entire global edge network to immediately forget specific content and fetch fresh copies from your origin. The fundamental challenge with the CDN is that once content is cached at edge locations worldwide, it stays there until its TTL expires. This is great for performance but problematic when you need to update content immediately, like fixing a critical bug in JavaScript, updating pricing information, or removing sensitive content that was accidentally published. Cache invalidation solves this. It forcefully evicts content from all edge caches before their natural expiration. The next user request for that content will trigger a fresh fetch from your origin server, ensuring everyone gets the updated version immediately. Understanding invalidation patterns is crucial for production operations. Single file invalidation is surgical and cost-effective. Wildcard invalidation is powerful but can create thundering herd problems where massive traffic suddenly hits your origin. Directory invalidation sits in the middle. It's useful for updating related content. Timing is critical with invalidation. The process isn't instantaneous. It can take 5 to 15 minutes to propagate across Google's global network. During this time, some users might still see old content while others see new content. Planning invalidation strategies around deployment schedules is essential. Cost considerations matter too. Google charges for invalidation requests, so using them judiciously is important. Smart versioning strategies can often eliminate the need for invalidation entirely. Invalidation commands. Surgical content updates. Let's dive into the practical mechanics of cache invalidation with real commands you'll use in production scenarios. The basic invalidation command targets your URL map, which represents the entire CDN configuration. The path parameter is incredibly flexible. You can target a single file, use wildcards for patterns, or invalidate entire directories. Single file invalidation is the most precise approach. Use this when you've updated a specific asset like a logo, CSS file, or critical JavaScript component. The path must exactly match what users request, including any query parameters if they're part of your cache key. Wildcard invalidation with the asterisk is extremely powerful but potentially dangerous. When you invalidate /assets/css/*, you're telling every edge cache worldwide to forget about every CSS file in that directory. The next requests will all be cache misses, potentially overwhelming your origin servers. The host parameter is mandatory and must match exactly what's configured in your load balancer. If you serve multiple domains from the same CDN, you need separate invalidation commands for each domain. Directory-level invalidation without wildcards only affects the exact path specified. This is useful for invalidating index pages or specific API endpoints without affecting related resources. Understanding the blast radius of each invalidation type helps you choose the right approach. Single files have minimal impact. Wildcards can create traffic spikes, and targeted directory invalidation offers a middle ground. Invalidation monitoring. Tracking global propagation. Monitoring invalidation status is crucial for operational confidence. You need to know when your invalidation has fully propagated before declaring an incident resolved or a deployment successful. The list invalidations command shows all recent invalidation operations for your URL map. This historical view helps you track what's been invalidated, when, and by whom, essential for debugging and change management. The output includes several key fields. The ID is unique for each invalidation operation. Status shows whether the invalidation is pending or completed. Timestamp tells you exactly when the invalidation was requested, which helps correlate with deployment times or incident timelines. Pending status means the invalidation is still propagating across Google's global network. During this time, some edge locations might still serve cached content while others fetch fresh content from your origin. This can create temporary inconsistencies in user experience. Completed status indicates the invalidation has fully propagated worldwide. At this point, all subsequent requests should fetch fresh content from your origin. However, content that was already cached in users' browsers will still be served locally until browser cache expires. Typical invalidation propagation takes 5 to 15 minutes, but can occasionally take longer during high traffic periods or network issues. Setting appropriate expectations with stakeholders about invalidation timing prevents unnecessary escalations. For high-stakes deployments, I recommend watching invalidation status before declaring success. Automated deployment pipelines should include invalidation status checks to ensure cache updates complete before the deployment is marked successful. Signed URLs. BIP tickets for private content. Signed URLs represent one of the most sophisticated features of Cloud CDN, enabling secure access to private content without requiring user authentication. Think of them as VIP concert tickets. They grant time-limited access to specific content and cannot be forged. The fundamental problem signed URLs solve is this: how do you serve private content through a public CDN? Traditional approaches require users to authenticate with your application first, but that adds latency and complexity. Signed URLs let you pre-authorize access and embed that authorization directly in the URL. The security model is elegant. Your application generates URLs with cryptographic signatures using a secret key that only you and Google know. When a user requests content with a signed URL, Google's Edge Cache validates the signature and expiration time before serving the content. Invalid or expired signatures result in 403 forbidden errors. Common use cases include premium video content, user-specific profile images, confidential documents, software downloads for licensed users, and any scenario where you need CDN performance for content that shouldn't be publicly accessible. The time-limited nature is crucial for security. URLs expire automatically, limiting the window of access even if URLs are accidentally shared. Typical expiration times range from minutes for highly sensitive content to hours for general premium content. Key management is critical. You need secure storage for signing keys, regular key rotation policies, and careful access control for systems that generate signed URLs. Compromised signing keys require immediate rotation and invalidation of all existing signed URLs. Signed URI implementation. Security through cryptography. Let's implement signed URIs from scratch. We'll cover both the Google Cloud setup and the application-side URI generation that makes it all work. The signing key creation is the foundation of the entire system. The OpenSSL command generates a cryptographically secure random key. This key must be stored securely. Treat it like a database password or a PI secret. In production, use Google Cloud Key Management Service or similar secure storage. Adding the signing key to your backend service establishes the trust relationship between your application and Google's CDN. The key name parameter lets you have multiple keys for rotation purposes. This is a critical security practice for production systems. The cache max age setting controls how long signed URI responses are cached. This creates an interesting trade-off. Longer cache times improve performance but mean content stays accessible even after the signed URI expires. Typical values range from 1 to 24 hours, depending on your security requirements. The gcloud compute sign URI command demonstrates the URI generation process, but in production, your application code performs this function. The signing algorithm uses HMAC SHA-1 with your secret key to create tamper-proof signatures. Expiration handling is crucial for both security and user experience. Short expirations, minutes, maximize security but might cause issues if users have slow connections. Longer expirations, hours, improve usability but extend the security window if URIs are compromised. URI structure matters for debugging and monitoring. Signed URIs include the original URI plus 3 additional parameters. Expires, which is a Unix timestamp. Key name, which indicates which key to use for validation, and signature, which is the cryptographic proof of authenticity. Production considerations include monitoring for signature validation failures, implementing key rotation procedures, and handling edge cases like clock skew between your servers and Google's validated. Key rotation. Security through regular updates. Key rotation is one of the most critical security practices for signed URLs in production environments. Just like changing passwords regularly, rotating signing keys limits the damage if a key is ever compromised. The challenge with key rotation is maintaining service continuity while enhancing security. You can't simply delete an old key and replace it immediately. There might be thousands of valid signed URLs in circulation that were created with the old key. These URLs need to remain functional until they naturally expire. Google Cloud supports up to 3 signing keys per backend service specifically to enable smooth rotation. The recommended pattern is to add a new key, update your application to use the new key for generating URLs, wait for all old URLs to expire, then delete the old key. Timing considerations are crucial. If your signed URLs typically have 24-hour expiration times, you need to wait at least 24 hours after stopping use of an old key before deleting it. This ensures all URLs generated with the old key have naturally expired. Monitoring during rotation is essential. Watch for signature validation failures, which might indicate timing issues in your rotation process. Also monitor the mix of keys being used. You should see traffic gradually shift from old to new keys over time. Emergency rotation procedures are important for security incidents. If you suspect a key has been compromised, you can immediately delete it, but this will break all existing signed URLs created with that key. Plan for this scenario by having communication strategies ready for affected users. Production monitoring. Visibility into CDN performance. Comprehensive monitoring is essential for maintaining CDN performance and troubleshooting issues before they impact users. The metrics and logs available through cloud monitoring provide deep insights into cache behavior, traffic patterns, and system health. Cache hit ratio is the most important CDN metric. It tells you what percentage of requests are served from edge caches versus your origin servers. Healthy production CDNs typically see 85 to 95% cache hit rates. Lower ratios might indicate misconfigured cache headers, frequently changing content, or cache key problems. Request volume monitoring helps you understand traffic patterns and plan capacity. Look for unusual spikes that might indicate viral content, DDoS attacks, or application issues. Geographic distribution of requests can inform decisions about new edge locations or origin server placement. Error rate monitoring is crucial for operational health. Watch for increases in 400x or 500x errors, which might indicate origin server problems, misconfigured URL maps, or issues with signed URL validation. Geographic patterns in errors can reveal regional infrastructure issues. Latency metrics show the user experience impact of your CDN configuration. Compare response times from different edge locations to identify performance bottlenecks. High latency from specific regions might indicate the need for additional origin servers or edge cache tuning. Security monitoring includes tracking signature validation failures, unusual access patterns to signed content, and potential abuse of CDN resources. These insights help you refine security policies and identify threats early. Log analysis provides the deepest insights into CDN behavior. HTTP access logs show exactly what content is being requested, from where, and how it is being served. This data is invaluable for optimizing cache policies and understanding user behavior. Troubleshooting. Systematic problem resolution. Effective CDN troubleshooting requires a systematic approach because issues can manifest at multiple layers, such as DNS, SSL, load balancing, caching, or origin servers. Having a structured diagnostic process saves time and prevents overlooking critical problems. Start with basic connectivity testing using curl with verbose output. This reveals SSL handshake issues, DNS resolution problems, and basic HTTP response behavior. The age header immediately tells you if the CDN is working. Age 0 means origin hit, positive age means cache hit. SSL certificate problems are common sources of CDN issues. Check certificate validity, domain matching, and certificate chain completeness. Google managed certificates can take hours to validate, especially for new domains or complex DNS setups. DNS configuration errors prevent traffic from reaching your load balancer. Verify that your domain's record points to the correct load balancer IP address. Use DIG or NS lookup to check DNS resolution from different locations worldwide. Cache key mismatches cause unexpectedly low hit ratios. Review your cache key policy settings, including or excluding query strings, headers, or protocols can dramatically affect cache behavior. Inconsistent cache keys mean content gets cached multiple times unnecessarily. Origin server health issues affect CDN performance even with high cache hit ratios. Monitor backend service health checks, instance group status, and origin server error rates. Failed health checks remove backends from rotation, potentially overloading remaining servers. Geographic performance issues require region-specific testing. Use monitoring tools from different continents to identify edge locations with poor performance. Sometimes the solution is adjusting traffic routing or adding additional origin regions. Production best practices. Lessons from the field. These best practices come from years of production CDN deployments and the painful lessons learned when things go wrong. Following these guidelines prevents most common CDN issues and ensures reliable, performant content delivery. Origin server configuration is the foundation of good CDN performance. Set appropriate cache control headers for different content types. Use long TTLs for static assets like images and CSS, and shorter TTLs for dynamic content like API responses. Use e-tags and last modified headers to enable conditional requests and reduce bandwidth. Health check configuration must be robust and representative of actual application health. Check critical dependencies like databases and external APIs, not just web server responsiveness. Failed health checks should accurately reflect when an instance can't serve traffic properly. Load balancer configuration requires careful capacity planning. Size backend instances appropriately for expected traffic, including traffic spikes during cache misses after invalidations. Configure connection timeouts and retry policies to handle temporary backend issues gracefully. Security configuration should be defense in-depth. Use CloudArmor for DDoS protection and rate limiting. Implement proper CORS policies for cross-origin requests. For signed URLs, rotate keys regularly and monitor for signature validation failures that might indicate attack attempts. Monitoring and alerting must be comprehensive and actionable. Alert on cache hit ratio drops, error rate increases, and performance degradation. Set up geographic monitoring to catch regional issues early. Use log analysis to understand user behavior and optimize accordingly. Change management processes prevent configuration drift and enable quick rollbacks. Use infrastructure as code for CDN configuration. Test changes in staging environments that mirror production. Plan invalidation strategies for deployments to ensure cache consistency. Disaster recovery planning includes strategies for origin failures, CDN service issues, and security incidents. Have procedures for emergency key rotation, traffic failover, and communication with affected users during incidents. Conclusion: your CDN journey forward. We've covered a comprehensive journey through Google Cloud CDN, from basic concepts to advanced production implementations. You now have the knowledge and practical skills to design, deploy, and operate CDN solutions for any scale of application. The key takeaways from our session represent the most important lessons for successful CDN implementation. Understanding the fundamental cache hit versus miss logic helps you optimize for performance. Knowing how to choose the right origin architecture enables flexible, scalable designs. Mastering security features like signed URLs opens up new possibilities for private content delivery. Operational excellence comes from applying the monitoring, troubleshooting, and best practices we've discussed. CDN is not a set and forget service. It requires ongoing optimization, security maintenance, and performance tuning to deliver maximum value. Your next steps should focus on practical implementation. Start with a simple static content CDN to gain hands-on experience. Gradually add complexity with dynamic origins, signed URLs, and advanced caching policies. Each implementation teaches lessons that improve your next deployment. The CDN landscape continues evolving with new features, security enhancements, and performance optimizations. Stay current with Google Cloud announcements, participate in the community, and share your own experiences to help others on their CDN journey. Remember that great CDN implementations are measured by user experience, not just technical metrics. Focus on delivering fast, reliable, secure content to your users worldwide. The technical complexity we've covered today serves that ultimate goal. Thank you for joining this comprehensive exploration of Google Cloud CDN. You're now equipped to transform your applications with global content delivery that scales from startups to enterprises. The world of fast, reliable web experiences awaits your implementation. Please subscribe if you haven't done so yet. Thank you.